All right, good morning, everyone. Thanks for joining FlexTrain. So as we continue our evolution of refrigerants, let's go back to where we started. So we started with our caustic, toxic, volatile refrigerants, the different chemicals like ether and CO2 and ammonia that we started working with way back when. And then as we got to 1928, we started developing our chlorofluorocarbon refrigerants and our hydrochlorofluorocarbon refrigerants. And then as we started realizing the potential for the destruction of the ozone with our CFC and HCFC refrigerants, we started moving away. We started removing the chlorine and we started removing the fluorine. So we had HFC refrigerants, and then we started looking at newer refrigerants or the use of refrigerants that we hadn't used in a while. So we started expanding the use of HC refrigerants. Hydrocarbon refrigerants. Now remember, those hydrocarbon refrigerants have been around for a very long time, but we got away from them because of their flammability. Well, now that we have refocused our efforts on understanding refrigerants as how they affect the ozone layer and how they affect global warming potential, we've relooked at hydrocarbon refrigerants. So the main thing that brought us into the hydrocarbon revolution is when we go back to October 15th, 2016. So 197 countries along with the US met, and they made adaptations to the Montreal Protocol, which became the Kigali Amendment. And under that amendment, the countries committed to cut the production and consumption of HFC refrigerants by more than 80% over the next 30 years. So that left us in a predicament. HFC refrigerants had become the modern staple of our refrigerant lineup. So we had basically 30 years to remove HFC refrigerants. Very ambitious feat. So what we were doing was we were trying to remove the potential for up to 80 billion metric tons of carbon dioxide equivalent emissions by 2050 and avoid up to a 0.5 degree Celsius warming of the planet by the end of the century. So phasing out the HFCs was really about phasing out the fluorine. We'd already made huge efforts to phase out the chlorine. Now we're making efforts to phase out the fluorine, which didn't leave us with a lot to work with. So hydrocarbons was one of the items that we had that we could work with because they have a very low global warming potential. So this week we're going to talk about the hydrocarbons and how they started moving into the industry and their limitabilities and their capabilities. So when the hydrocarbon refrigerant started becoming a necessity for the evolution of refrigerants, we had a lot of major manufacturers jump on board fairly early in the program, a lot earlier than most people realized. So True was one of the earliest manufacturers of equipment here in the US that started using hydrocarbon refrigerants. And one of their early advertisements was this one. It was an environmentally friendly hydrocarbon refrigerant, more efficient equipment, and no more harmful CFCs. So they started manufacturing equipment that had hydrocarbon refrigerants. And they had some training, and I've actually got in your material drop-down tab, you should have an additional training material that was a R290 training from True. So we knew that we had to make some changes in our refrigerant, and True was really making an effort to get ahead of that, and they were committing to making valuable contributions to the industry. And with CO2, it was a good alternative to use, but it had a very high operating pressures. So hydrocarbons were really the primary resolution in these small capacity refrigeration systems. So far, we produced over 2 billion hydrocarbon refrigerators and freezers used in homes worldwide. And True has had 20 plus years of hydrocarbon adaptation in Europe with over 4 million commercial units in use throughout Europe. So it's became an evolution of necessity to move into hydrocarbons. So, what is a hydrocarbon refrigerant? Well, the refrigerants they're natural, they're non-toxic refrigerants. They have no ozone depleting potential. They have very low global warming potential, and they're one of the most climate friendly and cost-effective refrigerants to cool and freeze with. So R290 is the primary refrigerant that is being used by True, and we'll see a couple others into play. And really what we're going to see is primarily R290 and R600, and we'll talk about those here in just a second. So we also had companies like Danfoss making commitments to move away from the CFC, HCFC, and HFC refrigerants. And so they started manufacturing equipment that would work with R290, which is purified propane, the same type of propane that we use for filling our grills that we cook with, but is very purified. So we add like sulfur dioxide and different chemicals to propane so that it has an odor to it, so that we know when we have a leak at home, right? Well, in the refrigeration world, it does not apply. So in the refrigeration world, we're looking for no impurities. So our HC refrigerants are going to be colorless and they're going to be odorless as well. So we have R290, which is purified propane. We have R600A, which is isobutane. We actually have R600, which is regular butane, not the isotrope of it. And then we also have one called R1270, which is a purified propylene. And we'll dive into that one here in a minute because that's one of our more unusual refrigerants in our HC lineup. So propane, it's been discussed since the late 1980s as a replacement for all these refrigerants. And so they did. They started manufacturing equipment really in the 1990s. We started getting into equipment that was using R290 and some R600. And what people don't realize is how fast we actually made that evolution into HC equipment. So the first hydrocarbon refrigerated equipment that I ran into was actually in checkout lanes at grocery stores. And they were about 10 years ago or so. I was trying to find the exact date that True released that, but it was somewhere around 2011, 2012 that they started introducing the R290 refrigerators in two-door variations. That was the first one that I had seen. So anytime you went through a grocery store that has a soda cooler, one of those sliding door soda coolers that's been manufactured in the last 10 years, it actually has R290 in it. We phased out 134A a long time ago with some of our hydrocarbon refrigerants. And so we had companies like Danfoss getting into the game early. We had True getting into the game early. We had Emerson getting into the game early. And so a lot of manufacturers of equipment started looking at the replacement of their HFC compressors with HC style compressors. But there were some things that needed to be adapted along the way. So our base hydrocarbon refrigerants really are methane and ethane, R50 and R170. And what we do to get the propane, butane, and the isobutane formulations is we're bonding the carbon molecules of those elements so that we get new variations of those. So you'll see like with our butane, we're going to be bonding 4 carbon molecules, and then we'll have hydrogen molecules bonded to the outsides of those. So the actual chemical formulations of those will be based on how many carbon molecules and how many hydrogen molecules. But they all really do come back to some variation of methane or ethane. So we have R50 for methane, we have R170 for ethane, 290 for propane, 600 for butane, and 600A for isobutane. Now, there is one other interesting refrigerant mixed into this entire scheme of HC refrigerants, and it's called R1270. So R1270 is actually a purified propylene. It is a refrigerant grade propylene, which can be used as an alternative to R22 in low temp and medium temp refrigeration and air conditioning applications. We don't see a lot of it out there, but it is around, and you're going to see a little bit of it going forward. So when you see R1270, be aware that it is a purified propylene, but it is in the HC class of refrigerants. So what happened was, in a long-awaiting move, the U.S. Environmental Protection Agency, they published an update to their HC class in 2017 to be able to move the capacities. Because remember, when we first introduced hydrocarbon refrigerants, we only allowed 57 grams, very, very small amount of refrigeration capability. Couldn't power a lot of equipment with that. So in 2017, we increased that from 57 grams to 150 grams. And that allowed us to have a larger charge of R600, R290, and R441 in our equipment. So what does that equate to? How much refrigerant can we put into a system? So we are allowed by law 5.29 ounces of our flammable refrigerants into a piece of equipment. So we currently do not have the capability of creating larger scale air conditioning or comfort cooling equipment that can handle the capabilities of larger capacities. We're limited to capacity because we're limited to the amount of BTUs that we can transfer. So we can create equipment that can have up to 5.29 ounces of refrigerant. So the refrigerants that we're going to be using in those HC classes are going to be these. So there is the 441A, which you'll see, which is a very interesting blend of refrigerants. It's an ethane, propane, butane, and isobutane mixture. Very new to the industry, being used currently with domestic refrigerators and freezers, vending machines, and self-contained commercial refrigerators and freezers. It is a high temperature refrigerant, high pressure, and it's an A3 class. All these are going to be A3 classes, which we'll cover here in a couple of weeks when we go through the different scales of volatility and flammability. We have R170 ethane, we have R290 propane, and we have R600 isobutane. And you'll see the zeros there represent the ozone depleting potential because we got rid of the chlorine. And we do have a small amount, a very trace amount of global warming potential with our refrigerants, but all of those are very low. If we remember R12, we were talking about 12,000 on our global warming potential. So that is a representation in comparison to carbon dioxide and its effect on global warming. So very, very low numbers with these, but they're primarily used for refrigeration. We don't have a lot of commercial or residential air conditioning applications, but we can create some fairly large pieces of equipment with 5.29 ounces of refrigerant. Currently, the largest one that I have found on the market is the 72 series. So that would be 72 cubic feet of space inside of the piece of equipment. So we're talking a 3-door cooler or a 3-door freezer, all capable of running with 5.29 ounces of R290. That's a pretty significant size piece of equipment. And that's a piece of equipment when we were running on R22 that would have probably had 1.5 pounds or so, maybe a couple pounds of refrigerant in it. So we have been able to modify our refrigeration processes to be very efficient with a small amount of refrigerant. So 5.29 ounces is all it takes to run that 3-door commercial freezer. That's a pretty significant improvement. So let's talk about that R441 that's in there. R441 is a very unique blended refrigerant built by a company called Comstar, and it's been marketed here in the US and in Europe. And it is a blend of ethane, propane, isobutane, and N-butane, natural butane. So it's already received approval by the U.S. Environmental Protection Agency to be used in refrigerators and standalone freezers and vending machines. So if you're out in the field and you see these coolers called MTL Cool, those are actually being powered by this 441. You'll see it with 2 different trade names, R441A or HCR188C. So they are the same refrigerant, and they're also approved for new window air conditioners and can be retrofitted into automotive air conditioning systems, which I thought was really interesting. I don't know that that's been approved anywhere, but it is capable of being retrofitted into automotive air conditioning. So that is the first A3 refrigerant that I've ever seen that can be used in an automotive application. And we can also use it in refrigerated transport systems like commercial refrigerators and freezers and showcases. So an interesting new refrigerant that I was actually completely unaware of until I started doing this research, because I'd never heard of 441. So what is that? Well, it's a blend of all of the other flammable refrigerants, and because it is a blended refrigerant, it adds new properties which help the travel and the return of oil in our system, which is what has given it the capability of being used in other products besides basic refrigeration. And it has some very good characteristics of operation. In this particular example, it came from their website, which is hcr188c.com. And you'll see, in comparison to an exact same piece of equipment, one running with R134A, one running with the 441, and the very curious thing about 441 is that it only needed 25% of its 134A's charge. That's a pretty efficient refrigerant, a fourth of the capacity to get the same cooling effects. and had pretty much the same operating specifications. All of our temperatures maintained in the refrigeration and in the refrigerator and the freezer sides. And if we look at that, we're actually only running a discharge temperature of 136, so it's a slightly elevated discharge temperature. But look how low our amps have actually been reduced on that. Our wattage is being reduced. So we've got 135 watts being used with 134A, and we're only 91 watts on a fourth of the charge. And it's maintaining a suction pressure
of 10 psi
and a discharge pressure of 135. That's a pretty interesting operating range. I kind of like that. That's good for a piece of equipment. We slam CO2 in there, we're probably talking about a 1200 psi head pressure. So operating pressures and temperatures are really important in our systems. So finding refrigerants that can operate with low pressures and maintain the temperatures properly is what we're looking at going forward. So that R441 is a pretty significant candidate for R134A replacements. We're already using R600A in most of our domestic refrigerators. Refrigerator here in my house, that's an R600 refrigerator. So it is an A3 refrigerant. So in the same comparisons, we can see that the R441 actually was able to outperform 134A at a fraction, 25% of its original charge. Now, when we get into working on these flammable systems, because we're talking very flammable refrigerants, we have to make sure we're using the proper equipment when doing that. If we think about a standard refrigerant leak detector, a lot of times we're using a heated anode or heated cathode style leak detector to find those refrigerants, right? Well, we don't want to introduce a heated element into a flammable refrigerant if we're looking for a leak. Otherwise, we're going to have a flame, right? So we're going to have to make a shift with our leak detectors when we're working with HC refrigerants. So JB has already gotten ahead of the game, and they've modified combustible gas leak detectors to be properly used with our HC, our hydrocarbon refrigerants. So we will be using a combustible gas leak detector as our standard leak detection device for HC refrigerants. So we carry that one in stock here at Johnstone Supply. It is rated for R290 propane. It's rated for R600A isobutane. It's rated for R600 butane natural. It's rated for LPG, ethane, R170, as well as acetylene, methanol, acetone, and gasoline, and comes with 300-hour sensor life. So be aware that when we are working with R290, R600, R170, 441, anytime we're working with these HC refrigerants, we have to pay special attention to the tools that we're using. If you look in that True manual for the R290 training, you'll see that True doesn't even have a recovery machine recommendation for that. No manufacturer does at the moment. So what they're providing, if you're wanting to recover, now remember, our A3 refrigerants, because they have such a low global warming potential and no ozone depleting potential, it's not required to be recovered. But if you want to, you can. So what True is recommending is that you purchase their R290 recovery equipment, which is literally anyone that's been out in the plumbing industry recognizes that housing. You know, that is a standard filter housing that we are now going to use with a specialized canister that will absorb the refrigerant and hold the refrigerant in a filter. So we're going to take this filter canister with a specialized filter. We're going to hook it up to a vacuum pump so that we put the canister in a vacuum, and they recommend at least 25 inches of vacuum before we start doing this. And then that way, when we connect our refrigerant manifold gauge and our hoses to the cylinder, we're going to draw in our R290, R600, whatever HC refrigerant we want into this specialized filter canister, and it will hold it for us so that we can then take it outside and release it, or we can reuse it if necessary. So that is the proper means of recovering 290. There's only one piece of equipment in the market that I found that is rated for high combustibility refrigerants, HC refrigerants, and that is this HC3. They call it a semi-automatic recovery system. That is available in the industry. It's not available to Johnstone currently, but it is the only certified HC recovery unit that I could find out there in the industry. It's being widely used in Europe, and I'm sure it's on its way to the United States. So here at Johnstone, we do carry these refrigerants in stock. We carry R290 with the part number B87486. We also carry R600A as a B87487. We also carry a hydrocarbon service kit from ICOR called the HC-Kit, KIT. And what that does is that gives you your R290, your R600. It gives you a label kit and gives you some access information, and also gives you a temperature data sheet. So through ESCO is providing some A3 certification, hydrocarbon certifications. And what they're doing is helping prepare technicians for the hydrocarbon class. It actually covers more of the A2L instead of the A3, but it gets you into that field. True used to have their own training program, and then they started recommending RSES for the training information on A3s and A2Ls. And since RSES is now adapted into ESCO, it's going to be part of their future lineup of courses. So if you're not comfortable working with A3, A2L refrigerants, just pay attention to ESCO, and I'm sure you're going to be seeing some certifications in the future that will have you prepared for A3 refrigerants. In the courses that they have through their A2L program right now, they do talk about a lot of things like proper identification of these refrigerants. So there are processes in play that will properly label these pieces of equipment. So on the tag, on the actual identification tag of the piece of equipment, you should see the ISO 710-W021 symbol, which is going to be for flame. So that will be your flame symbol on the actual ID tag. And on the piece of equipment itself, we're now requiring red markings to extend a minimum of 1 inch from every service access on that piece of equipment. So you'll see these red sleeves on the refrigerant lines, on those process stubs, and you'll also see the triangular flame symbol to represent that it has a flammable refrigerant in that system. Because the last thing we'd ever want to do is to be able to open up a system and have a torch on that getting ready to make a repair, not realizing that it was actually previously charged with a flammable refrigerant with up to 5.29 ounces of that flammable refrigerant. So just a little fun fact for the day, a little bit of education questioning. Have you ever thought about why it is easier to grill in the summer? Have you ever tried using a propane grill in the middle of winter? So I'm going to launch a real quick poll just to get a perspective on this, because it took me a minute to really think about that. And a couple of years ago, we started diving into why is it really difficult to use a grill in the winter? So is it because there's low pressure in the winter? Is it because there is high heat escaping from our piece of equipment in the winter because of the cold ambient temperatures? Or is it just more fun to grill in the summer than it is in the winter? I'll give it just a couple seconds. All right, that's a good one. So poll says 100% low pressure in the winter. And that is so true. So the interesting fact about refrigerants is that we all know they have a relationship between temperature and pressure, right? Well, let's put that into some practical applications when we're talking about these HC refrigerants. Let's take R290, purified propane. Because remember, the only difference between R290 and the propane that goes into our grill is that we add things like sulfur dioxide and other different chemicals to our propane so that it has an odor to it, so that if it leaks, we can detect it, right? So if we look at the temperature pressure chart of R290, we can see why our regulator works so hard to try to maintain that pressure. Because what kind of pressure do we really want at orifices? Somewhere between 10 and 14 inches, somewhere in that ballpark, right? Just like we were setting a pressure off from our gas valve on a furnace. That's what our gas valve is doing, is it's using a pressure regulator to maintain the pressure coming out of our gas valve so that we have a constant flame, so that we can maintain proper BTUs. Well, if we think about that, that's a relatively controlled scenario. The temperature coming into our gas valve or the pressure coming into our gas valve isn't altered drastically. It's relatively consistent. Well, if we look at the pressure coming into the regulator on a grill, on a propane grill, on a nice summer day, a 75-degree day, that tank actually has 119.5 psig of pressure on it. That's a pretty significant amount of pressure. So our regulator is trying to get us back down into that 10 to 14 inch range. So the diaphragm is floating around trying to find that 10 to 14. So it's got a, it's got a pretty significant pressure drop across that regulator. Well, what happens is as our temperature of our tank starts to decrease, so does the pressure on our tank, which means our regulator then is trying to flex a lot to be able to maintain that 10 to 14 inches of water column. So by the time it gets down to 30 degrees, I now only have 51.8, less than half of the pressure in my tank that I had on that 75-degree day. And if you're a silly goose like me and you're out there at 0 trying to grill, which sometimes happens, sometimes you just are craving some fresh meat on the barbie. At 0, we only have 23.7 pounds of pressure on that tank. So now our regulator is really flexing down, trying to maintain that 10 to 14 inches of water column. So temperature pressure relationship stays consistent with all of our refrigerants, including water. So R290 and R600 are no exceptions. They have a temperature pressure relationship. So as our temperature reduces, so does the pressure in our refrigerant in its boiling point. So that refrigerant is going to continually drop its pressure down to the point at -40, I only have 1.4 psi. I barely would have enough for my regulator to even do any work for me. So that is the reason we have an effect of cooking on our grill that is better in the summer, because we just have more pressure in the thing. All right, well, that's the end of the presentation for hydrocarbon refrigerants. I'm going to go ahead and open up the lines in case anyone has any kind of questions on HC refrigerants or comments.
It still fascinates me that five ounces is all they need to get that systems. That's such a small amount.
It's hard to fathom, especially on that 3-door freezer. I've worked on oodles of those things in my career, and 5.29 ounces might be how short it was to keep it operating, not a total refrigerant charge. So now we're getting into very, very critical refrigerant charges. 5.29 ounces on the dial-a charge would not have been a fun thing to try to operate on. It was designed for pounds of refrigerant. 5.29 ounces on a 72 cubic foot freezer. That is unheard of. I would be very curious to look at some old freezers and get some refrigerant charges, but I know for a fact that it was well over 2 pounds with R22. So it just shows how much more efficient these flammable HC refrigerants are over some of our previous refrigerants. So a very fraction of the amount of refrigerant is needed over our HFCs and our HCFCs and even our CFCs, which I previously thought would have been our best refrigerants. So we can understand why these refrigerants have been used for 100 years or more, but we didn't stick with them because of their flammability. And now that we are refocusing on the effect of the ozone and the effect of global warming, now they're becoming more practical for use. All right, good stuff, everyone. I appreciate everybody joining us, and we'll see you next week as we talk about the other class of refrigerants called HFOs, hydrofluoroolefins. And you'll be surprised to see that they're already in use, and they've been in use for a few years, and most people didn't even realize it. So everyone have a great day, and we'll see you next time on FlexTrain.